Hello all. In this video, I'm going to introduce the concept of image masking, and then later on we'll also look at how we can generate masks or other black and white images for other reasons using various thresholding functions. I have several different code examples. These are mostly drawn from your readings, and I'm going to walk through those and try to explain them and just kind of get at the basic ideas. All right, so why are we doing? Where are we? We've been talking about a lot of Python programming thus far, and then we've started to transition. We're going to spend much more time learning about computer vision and how it works. We started that by looking at image arithmetic. So what does it look like when you add a number to an image, or you use blending to try to merge two images together? There are a couple of different functions we learned for OpenCV there. This is the start really of a series of topics that are about image manipulations, so image processing, but it's steps we need to take in order to write computer vision programs that are able to actually extract information from an image. And really that's what's critical. That's what we want to do with computer vision. We want to be able to get information out of an image and use it in some form. So just to make clear what I mean by that, what does it mean to get information out of an image? It could be separating the objects in an image. So identifying which pixels in an image are person versus chair versus tree versus sky, being able to label and identify all the different parts and the shapes that they are, identifying where a specific object is in an image, and it could be a type of object, so you want to identify all books that appear in an image, or maybe you want to identify a specific thing like a specific book and not any others. Those are both computer vision tasks. Being able to recreate a 3D approximation of a 2D image, that's one of the more complicated and difficult tasks to do. Recognizing when two images are of the same location and being able to tell how they differ from each other. There are lots of other examples, but these are just sort of some examples of what you have to do, or what we might like to do with computer vision. The problem for the computer, and we're going to spend some time early on here not talking about machine learning, deep learning approaches to these problems, because they build on some of these ideas in a way that make these ideas important to learn, but they're also not always the correct solution for every computer vision application. But when we don't have machine learning to do some of this work for us, the issue we run into is that normal photorealistic photographs, images that look like photos, they're very hard for a computer to manage because there's a lot of variability that we don't even notice that makes it difficult. To the computer, an image is just a box of numbers. It's a box of numbers between 0 and 255. And if you have a color value that's just a little different than the color next to it, those differences are apparent to the computer. How can we make them less apparent? Well, we do a lot of this kind of image processing. So the tools we're looking at today and going forward, many times the reason we do these tools is that we want to simplify the work for the computer vision program. We want to modify the image so it's easier for the program to work with it. There can be other reasons as well. You could just be looking for interesting image effects, or just trying to decorate an image. There are lots of things like that you could be doing as well. But the primary one is simplifying things so that the computer vision programs work better. All right, we're going to talk about masking first, so building mask images and applying them to other images. So what exactly is a mask? A mask is a black and white image. It may be the shape of a color image. It could be that it has the blue, green, and red channels like all of the color images. But every pixel is typically set to either completely black or completely white. And we treat it as a way to block some of the content of the image. which is a really great way of simplifying an image and making the computer focus on only certain things. If you cover up the parts you don't want it to focus on, then it won't focus on them, and it will be forced to focus on only the parts that are left. So I have a physical example here that I wanted to use because I think it's sometimes easier to see what's going on with that. So suppose I have here, this is one of our images. I'll move back a little bit so you can see it. So this is one of our images that we've had in our sample images. It's a normal photograph. Suppose that I want to limit the picture so that only some parts of it are showing. Then I build a mask. In the physical world, a physical mask looks something like this. This is a black and white piece of paper that has had holes cut into it. And you notice I have sort of a trapezoidal hole here, and I have almost like a little diamond shaped hole. Can I put it somewhere you can see it? A little diamond shaped hole down in the corner. So this is my mask. When you apply a mask to a picture, you basically take your picture and place the mask over it. Now, this implies certain things. It implies that the mask needs to be the same size as the image. But then notice what happens when I put the black paper in front of the picture. Only the little section down here and the irregular polygon in the middle are actually remaining. All of the other parts of the image have been masked away. They've been blocked from view. That's what a mask does in the physical world. That's what we do in the digital world as well. Our black and white image is treated just like that black piece of paper. When I apply that mask to an image, what happens is the parts of the image that are the same location as black pixels in the mask just stay black. And only where the mask is white do the pixels from the original image actually show through. All right. We can make a mask in two different ways. We can make a mask by hand. So I made this paper one by hand. I cut shapes out of a black piece of paper. Inside the computer, what does that look like? Well, you make a black image, which we've done before, the same size as your original image that you want to mask, and then you draw white shapes on it using the drawing functions that we've already learned. So I can draw a big rectangle in the middle if I just want that middle rectangle to be visible. Anywhere that I draw a white shape, that's part of what will actually show through. The second approach is programmatic. So we could write a program that will process our original image and generate a black and white image from it. And then we could use that black and white image as a mask. And we'll see some examples of that. The thresholding that we're going to do in a little bit is that approach. What I want to look at first is this first approach. And that's where we have a couple of code examples to take a look at. Okay, so this first example, this is again an example from the reading, but I want to talk through it in some detail. What we're going to do is to create a mask that's a little silly. It just has some circles drawn on it, but we'll use it as a mask and we can see what that looks like. So I've got the original image. I'm reading in our picture of the Teton Mountains. And then here is how I can make a new black image the same size and shape. So I say np.zeros. We've used that function before. We say origimage.shape. This says make the new one the same shape as the original one. And origimage.dtype says and the same data type. I could also have just written np.uint8 because all of our images are uint8 unsigned integers, 8 bits long, but this also works. This is going to be our mask image. The next steps are I'm going to draw some shapes onto the mask image. So I'm going to draw a rectangle at a particular location, and then here I'm drawing 3 circles. They're all the same size, but they are at different X locations across the image. And that makes my mask image. And then I'm going to scroll down a little bit. The stuff down below this line, that's our next example, so don't pay attention to that. Here is where we apply the mask to the image. And this is a strange notation. Bitwise AND is an operator I don't really want to fully explain to you. I'll just say that what it does is it does an AND operation on the bits themselves. But what happens is if we have white pixels in the mask, then when we bitwise AND that with the color of the original image, we get the original image's color. And if we have black pixels in the mask, then when we do a bitwise AND with the original image's color, we get black. So it does exactly what we want. It keeps the original colors anywhere there's white in the mask, and otherwise it sets the pixels to black. All right, I want to run this and take a look at what it does. That means I'm going to have to shift to my full screen. So just a moment while I do that. All right, I made the code just a little bigger so you might be able to read it even when it's on my full screen. And on this screen again, I'm going to move myself over to the corner. All right, so now we're going to run mask example. And we'll see the result from the first step. So here I have our original picture. That's our Grand Teton picture. This is the mask that I created. I drew a rectangle down the bottom. I drew 3 circles across the top. When I apply the mask to the image, I get this result. This is the masked image. You can still see the parts. It's as if we're holding up a black piece of paper with those labels on it while we look at the scene. All right, that's a simple example of what we want to do. We can make mask images from scratch just this way, just by drawing out rectangles and circles on a black image. And then to apply the mask to an image, for the most part in OpenCV we'll be using bitwise AND. There are other ways to do that, but the main one that we'll use is this bitwise AND operation. And then we get a nice result that's been masked. There's one other example that I want to come back to. I may leave this code at the larger size unless it looks too ridiculous. We had just learned about connecting to the video, connecting or writing code that connects to the video on the webcam on our computer, and then we can do things with that to manipulate the resulting images. So I decided to do an example. This got way more complicated than I wanted it to be, so I'm not going to explain exactly everything in this video. But I'm setting up a connection to my webcam. I'm setting up some variables here. Some of these are going to change and some of these are not. Fundamentally, I want to draw a rectangle on the video feed, and I'm going to mask the image so only that rectangle shows. So this is the upper left-hand corner of the rectangle when I create it. This is how wide it will be, how wide and tall. I guess it'll be a square. And with each frame, the rectangle is going to move. So it will move in the X direction by 5 and in the Y direction by 5. So I'm just setting up some things here that allow me to specify the movement that's going to happen. Inside we have a loop that goes through the frames. So if you remember, this command is going to read a frame from the webcam. And assuming all goes well, that will be in the variable frame. Hello there. I'm sorry. I realized that this code was written slightly differently than the earlier example, and I thought I'd just stick with the simpler example. And I also realized that my square size was a little small for the camera that I'm currently working on. So I increased the square size, so it'll be 700 by 700 pixels. All right, so in here, I'm making the mask exactly the same way I did up above. I'm calling np.zeros, I'm passing it the image, the frame's shape, and telling it here I want it to be uint 8. And then I'm drawing a rectangle specified on the mask image, specified according to these variables that I set up above. These are all going to be in some way almost like accumulator variables. So square x and square y will be the upper left corner. Square x plus the square size and square y plus the square size will be the lower right corner. I'm specifying that the color is white and it's filled in. Then I'm applying that mask using Bitwise, and I'm applying that mask to the frame, and I'm displaying that instead. And I just have code here at the end. I have code here that handles so I can quit out of the program. There's some extra lines of code down here. I'm not going to talk about those right now. Those have to do with making the image bounce. I don't want to focus on that while we're just talking about masking, but I can talk about it separately. So let's switch over to the desktop view again, and I'll run this program again. So here's our original. We got the 3 results. Now let's go on. When I hit the next key, it's going to pop up another version of me that is being generated by Python. And you can see that there is, in fact, a bouncing square. Ooh, that one bounces kind of in a fun way. So it's bouncing around in the frame, and it's showing the part of the frame, but masking most of it away. My camera has a ridiculously high image size, which is why 700 by 700 is actually only a small portion of my video feed. And then I can hit Q at any time to end this program. All right, so this gives you a sense of how masking can be used. We can use it for a variety of purposes, both decorative and more often to be able to focus the computer on only certain regions. So one of the ways we can make the computer focus is by doing a region of interest, but here we can keep the original image and still only have some of the data available to the system. All right, before I end this video, I am going to talk about the bouncing thing, because that's important if you want to understand this program as a whole, although it's not particularly relevant to masking. So I set this up with a starting point, the XY coordinates, and this change. So if I go all the way down to the bottom of my while loop, you can see that I'm adding that change value to square x and square y. They are acting, in fact, exactly as accumulators. But the thing is that I want to make sure that the image stops moving in one direction when it gets to the edge of the frame. If I don't, it will just keep going on in the computer's mind when we just won't be able to see it. It'll just move out of frame and disappear forever. So I want it to bounce back. And there's a little bit of tricks to how you do this, but fundamentally, I need to detect that it's at the edge of the frame and then change the direction. And it turns out that I can do that with these 2 lines that are right here. So I'll look at the second part of this one first. If I'm looking at it touching the left or right edge of the displayed video feed frame, the left edge I would notice it because the square x value would go negative. It would go past 0 and become a negative value. And if that's the case, I want to change direction in the x direction, because that's the variable that's gone out. I want to change and now have it start moving to in the other direction. So if it goes off to the left, that means that the x value is getting smaller and smaller. We were subtracting from the x value each time. We're going to flip it around and add to the x value to make it move toward the right. The other bound is the width of the picture, and we look at the square size, square x value plus the square size, so the right edge of the rectangle that we're drawing. And if it goes beyond the width of the picture, we also want to flip the directions. It's just that in that case, it will have been moving to the right, and now we want to change and move to the left. So instead of increasing the x value, we're going to decrease the x value. And we do the same thing in the other direction. I recommend, if you really want to understand how the bouncing works, is take a small example and work it out by hand. Work it out on paper and make sense of exactly what's happening. If we are at one of the boundaries, all I'm doing is negating whatever the previous speed was. So it started as 5. When it gets to that right edge, it's going to flip the delta x to be -5. And then it'll start, every time we add delta x, it's actually subtracting. When we get to the left edge, we're going to flip it again to make it the negative of -5, which is +5, and then it will automatically start moving in the other direction. This is kind of magical. It's more simple than you might think just to make an object bounce. All right, I am going to stop there. In the next video, we will take a look at thresholding and a couple of different techniques for doing that. I will see you very soon.